When we looked at the classical wave equation, we saw that it generated conditions that would help us solve for not only the position dependence of the wave, but also its time dependence. This same is true in quantum mechanics, and this is the subject of Postulate 5. Basically says that the state of a quantum mechanical system can evolve in time, and it does so according to a very specific equation, namely the time-dependent Schrödinger equation, which is given here. Basically says that I h bar times the time derivative of the wave function will be equal to the operation of the Hamiltonian operator on that wave function. Now this should be distinguished from the version of the Schrödinger equation that we saw before that looked something like this. It was essentially an eigenvalue equation for the energy involving the Hamiltonian operator. Now, you might feel like this is a source of confusion now. We've got two different Schrödinger equations. But what I hope to show you is that these two are related to one another, and this one, in fact, represents a time-independent Schrödinger equation. So how can we get a handle on this? Well, the first thing we should do is to take our overall wave function, and I'm going to just use a single position coordinate, not three, because that'll make our formulation a little bit easier, and simply write this as the product of a position-dependent part and a time-dependent part. Now, we'll notice that this part is the only part that will be influenced by the time derivative of the wave function. So it'll only affect the t of t part, not the psi of x part. Similarly, if our h is time independent, that is to say it does not depend on time at all, we already know that the Hamiltonian can operate in various ways on the coordinate parts of the wave function, so it will affect the psi of x, but it will not affect the t of t. So now when I plug this product function into the time-dependent Schrödinger equation, I'll end up getting something that looks like this, and I'm going to put it in a little bit different color to contrast it. So I'll have I h bar times the coordinate-dependent part times the derivative of the time-dependent part is going to be equal to the time-dependent part times the operation of the Hamiltonian on the coordinate-dependent part. Okay, so we can see that the left-hand side operated really only on the time-dependent part, and the right-hand side operated really only on the position-dependent part. Now, as I did in the separation of variables technique, I'm going to divide this equation by the product of these functions. Okay, so when I do that, I'll end up with an equation that looks something like this. I'll have I h bar over t of t times dt dt is equal to 1 over psi of x times the operation of the Hamiltonian on psi of x. And just as we had in the separation of variables, we have one side that depends only on time and another side that depends only on position. Okay, so since this can vary independently from this, each side must be equal to a constant, so they're equal to the same constant. Now, having indicated that, let's take this right-hand side and see what that tells us. Well, if I multiply both sides of that by psi of x, I'll have h times operating on psi of x is equal to alpha, a constant, multiplying psi of x. Well, I hope we recognize that this is the eigenvalue equation for the Hamiltonian. So in fact, what we really need to consider are the eigenfunctions of the Hamiltonian. So what I really want to consider is this. And so that means that our coordinate-dependent parts will all have to be somehow either eigenfunctions of the Hamiltonian or written as some kind of linear combinations of the eigenfunctions of the Hamiltonian. All right, so if I have this psi of x in here, that means that alpha has to equal this constant E sub n. So now let me unpack the time-dependent part. So if I take this time-dependent function and set it equal to the nth eigenvalue, I'm going to rearrange this a little bit so that it looks something like this. When I divide dt by t, that's the same as d of log of this function. And then when I put everything else on the other side and do some proper manipulations, okay, when I divide by I, that's the same as multiplying by minus I. It's a useful trick to remember. but that's going to be equal to this dt. So when I integrate this equation, when I integrate the left-hand side, I'm going to get log of t of t over t of 0. And on the right-hand side, I'm going to get minus I e sub n over h bar times time. Okay, or formally time minus 0, but just time. Okay, so when I actually solve this for t of t, what I'd find is that the time-dependent part of this equation, and I'll put it in red over here to really emphasize it, the time-dependent part is just going to be its time-dependent part at time 0 times e to the minus I e sub n t divided by h bar. All right, now this part is basically an initial condition on this. We're going to take this part to just be 1 so we can ignore it. We can just say t of t is equal to this exponential. But that also means that the product of the complex conjugate of t with t is going to be e to the minus e sub n t over h bar times e to the minus I e sub n t over h bar. And when you multiply those two together, you'll just get 1. So what does that mean? Well, that means for all practical purposes that if I look at the square magnitude of my total wave function, that's going to be equal to the square magnitude of psi of x, t of t, which is just the square magnitude of psi of x times the square magnitude of t of t. You can usually divide these things down that way. But since this is 1, that means that our time-dependent wave function is simply got the same square magnitude as the time-independent wave function, psi here. So this Schrödinger equation that we developed earlier, is something that we can also term the time-independent Schrödinger equation. Okay, because it's going to generate the eigenfunctions of the Hamiltonian. But this function, since it does not depend upon time, and this does not vary with time, we call this function a stationary state. That is to say, it's not moving its probability density anywhere, it's staying fixed in time. All right, so when we are done with all of this, you may wonder, well, why are we bothering with this time-dependent part? Well, in general, we can write these a general state, psi of x and t. I could write this generally as a sum, a weighted sum, over all of the eigenstates times the corresponding time-dependent functions. Now I'm making this t sub n because there's an independence. That sounds like independent. There is a dependence on n here in the energies. So each of these time functions is actually different, and in fact we could write this more specifically like this. And so this, in fact, is what really gives us the time-dependent type wave functions, is taking a linear combination of the eigenfunctions of the Hamiltonian. And you would find that these then are perfectly legitimate solutions to the time-dependent Schrödinger equation. So this also tells us that maybe one way to solve the time dependence of a system is to decompose a more general function into the eigenfunctions of the Hamiltonian. Then we can readily write down how it changes with time. Now, if you're wondering when this might become useful, time dependence is mostly comes into play when we're doing things like absorbing light. So a spectroscopy experiment inherently involves the time-dependent Schrödinger equation. We won't actually show exactly how that happens when we talk about spectral results. We'll talk more about the energy gaps in the transitions, but it's useful for you to know that the time-dependent Schrödinger equation is a very important one when it comes to studying dynamical processes in systems.